Okay, it's time. Welcome back. We are going to continue talking about limits today. I said last time that I was going to record class every day and post it online after the fact. Last time it got messed up. I had some issues with my computer, so unfortunately the first time around didn't get recorded properly. But I figured it out now, so it's all going to be great from now on. You can see all those recordings at the class website, which is the link that's on the syllabus. All right. Let's talk a little bit more about limits on graphs. I hope that everybody remembers. In my opinion, what we did last time is fairly straightforward, as long as you can keep straight exactly what you're looking for in the picture. And what I want to talk about today is just a little addition onto that, or at least first, and then we're going to move on to something a little fancier. But I want to talk about one-sided limits. And this is another thing that we're going to do just by looking at a picture. And if you know what to look for, there's not really a lot to it. It's a fairly simple idea, in my opinion. So I'm going to take here's an example graph. How about, goes over here. Let's say like this. This again is one of those sort of empty circle, filled in circle. Jones. Is that what they sell? People say that? I've heard people say that sometimes. Philadelphia style. Yeah. I don't usually say that. It's maybe the first time I ever said that. Anyway, one of those Johns, where you got the filled in point and the empty point. And according to what we talked about last time, I could ask you what is, actually let's just ask, what is f of 3 versus what is lim x goes to 3 f of x. This is what we talked about last time. F of 3 means you look right at this point, x equals 3, and you say what's the y value? And I have the empty circle and the filled in circle. When I'm asking about what's the y value, you look for the filled in circle, not the empty circle. So I use this one, and I get 1 for f of 3. f of 3 equals 1. Because when you see the empty circle and the filled in circle, you choose the filled in circle. That's for what f of x is. And the limit as x approaches 3. Now for this one, you look along the curve in this area where x is 3. Along the curve, what is the y value? And in this case, you see a certain y value when you're on the right side of the curve, but a different y value when you're on the left side of the curve. And for that reason, we say that this limit does not exist. All right? And this is because the two sides of the curve go to different values. Two sides of the curve go to different y values. There's one on the right side and there's one on the left side. And in that case, we say that the limit overall does not exist. But if you want to get specific about it, you can say, well, there is one limit on the right side, which equals something, and there's another limit on the left side. And that's what this, that's what one-sided limits means. You can talk about, specifically if you want to, the limit on the right side and the limit on the left side. So in this case, we say, and it looks weird when you write this, but I'm going to say lim x goes to 3 with a little plus there. The little plus means the limit from the right side. That means near this point, you only look over here. And this plus is meant to indicate sort of on the x-axis, the positive side is on the right. So over here, and of course you always write f of x, the limit as x approaches 3 from the right of f of x, in this case, equals 2. That's because when you look on this side and you look along the curve, the y value approaches 2 from the right. That's what the little plus means. All right. So this right here, if you were to say this out loud, this is the limit as x approaches 2 or 3. Limit as x approaches 3 from the right. And in this example, that y value along the side from the right goes to 3. To 2. Sorry, I'm mixing up my 3's and 2's. All right. Along here, the y value approaches 2. Okay, and then we can also talk about the limit from the left. That's written in the same way, but with a minus instead of a plus. So that would be lim x goes to 3 from the left. And now for that one, you look along the curve on the left side. And that curve on the left side approaches 1. So I say this equals 1, the y value from the left side. I hope that seems clear to everybody. Anybody got questions at this point? We're going to do some more examples in case. All right. There's really not a whole lot more to say about this. Let's just try another example, and then I got one for you all to try, and then we'll go on to something completely different. So how about this? I'm just going to draw another weird picture here. We've been doing sort of nothing but weird pictures so far, but actually we're going to get to some equations as soon as we finish this last little bit here. I don't know if you like the pictures or not. How about this? All right. And we can ask about the left side and the right side limits. And we might as well talk about the overall limits also. So the interesting points here are like here where there's a point bumped up, and then here where there's actually a complete break in the line. So I'm going to talk about, let's talk about f of 1, and also lim x goes to 1 from the left, and also of f of x, and also lim x goes to 1 from the right of f of x, and then also just plain old lim x goes to 1. That means like the limit on both sides at the same time. If the two sides are different, you say that one does not exist. Anyway, let's just go down the list here. So what is f of 1 here? And want to show me the fingers? Show them if you got them. F of 1. I see some fingers. I see a lot of this going on. 3 is the answer. Right? F of 1 is 3. That means you look at x equal 1, you look up here and find the y value. You choose the filled in dot rather than the empty dot. So that one is 3. Great. How about limit as x approaches 1 from the left? That means I look nearby here, but on the left side. So I'm talking about this part of the curve. Since it's about lim, that means you should be looking along the curve. What is the y value that the curve goes to on this side? And I would say 2. Right? From this side, the y value approaches 2 as you get to this point. So this one here is 2. All right, that's the limit from the left side. Okay, what about the limit from the right side? So again, I'm looking near this point, but on the right side. That means right here. This is sometimes confusing. When it says from the right side, you don't necessarily go like all the way to the right, because this is some other business over here. You're really looking near this point 1, but only to the right of it. All right, anyway. Along the curve right here, where does the y value approach? And I would say it approaches 2, right there. It's actually the same on the right and the left. In this example, I mean, you can tell by looking. The curve is going the same place on the right and the left. So this one is also 2. That's from the right side. And then what about the limit overall? Well, if the two sides are both going to the same place, then that's where the function is going. And so this limit is 2. All right, the curve as a whole does indeed approach 2 when x is 1. All right. Okay, let's try the other one. Over here, this point, right? This is x equals 3. So we can also do f of 3. Lim x goes to 3 from the right. I did the left first. I might as well keep in the same order. Doesn't matter. Lim as x goes to 3 from the right. And then lim x goes to 3. This is like the overall limit from both sides. All right, what do we got? F of 3. That means you look at x equal 3, you find the y value, in which case you use the filled in circle, and I get 1 for the y value there. So this is 1. What about lim as x goes to 3 from the left? That means you look near this point, but only on the left side, which would be, you should be looking like right over here. Don't go all the way over here, way to the left. It's only slightly to the left of the point you're concerned with. And what's the y value the curve approaches? I would say 1. This curve approaches y equals 1 on this side. All right, so that's a 1. How about from the right? Anybody think you know? You should be looking near this point, but on the right, yeah.
0.
I would say 0, yeah. This curve on the right side here goes down to y equals 0. Great. And what about the overall limit? We have, actually, this can always be determined by looking at these two, the right side and the left side. In this case, they were equal, and so the overall limit is whatever that number is. In this case, they are different, which means the overall limit does not exist, because there is no specific value which is approached overall. There's kind of two different values. So this here, d and e, all right? And this is a general fact that's always true. If the limit from the right and the left are different, then this limit as x goes to, whatever point you're talking about does not exist. And if the limit from the right and the left are the same, then the limit does exist and it equals whatever those two other limits were. All right. Great. I got one for you all to try, and then we'll move on to something else. I hope everybody kind of agrees that this is straightforward enough. All you got to do is look at the picture and, correctly identify what you're supposed to be looking at. Here is one last weird picture example. All right, and I would like you to do all that same business. Let's try f of minus 1, also lim x goes to minus 1 from the left. Also lim x goes to minus 1 from the right. And lim x goes to minus 1. And then also for 0. All right, try it out. I'm going to walk around and see how you're doing. Like I said last time, I'm not trying to give you a grade or anything. Just make sure everybody is keeping with it. Staying on the journey. Feel free to talk to your friends if you got them. We're all friends here, right? So far. I'll give you another minute and then we'll chat about it. All right, can we talk about these? So, again, there's not a lot, ordinarily I would say you got to show your work for everything, although there's nothing to show really in these problems. You just look at the picture and say the answer. F of -1, that means I go over here, I look for the y value, I don't use the empty circle, I use the filled in circle, and it is -1. I hope that's what you got. F of -1 is -1. Lim x goes to -1 from the left. This is weird looking, this little -1 minus. That means near -1, but on the left side. So along the curve this way, on the left side, the curve goes to y equals -1. So this is also -1. I hope that's what you said. What about from the right side? From the right side, it's different. That would be looking right here, approaching this point. From the right side, it goes up to y equals +1. So this is 1. All right, and then what about the overall limit? Well, since I've already done the two sides, and the two sides are different here, that means the overall limit does not exist. And that's what I say. I hope that that's what everybody said. As I was walking around, it looked like people were getting this fine. I hope that's true. All right, and the other one, f of 0, that means you look here, you look up to the filled in dot, that's 2. Limit as x approaches 0 from the left. You look along the curve in this area, just to the left of 0, and the y value along this curve goes down to 0 when you get to this point. So this is 0. I hope that you got that. From the right side at the same point, that's here, but over on this side, I look along this curve. It also goes to y equals 0. And in this case, since the left side limit and the right side limit are both equal to 0, this one also equals 0, because these are the same. That's the same as the overall limit. All right, I hope everyone is clear on that business. Any thoughts? Great. All right, and here ends the discussion concerning number 1 on the big checklist, limits on graphs. This is all we're going to say about limits on graphs. I hope you all feel good about limits on graphs. What I want to start talking about next is, the next thing on the list. It's called limits algebraically. Algebraically, meaning not looking at the graph, but looking at equations. That's what I mean by algebraically. If I show you an equation of a function, can you tell me what various limits of that function will be? So that would look more like something like limit as x goes to 3 of, and I just tell you some function in here, all right? Now, one strategy would be to draw the graph of that function and then look at the graph, but this is usually not what you want to do, because if I just give you some random function here, it's unlikely that you even know how to draw the graph of it without using your calculator or something, and I don't want to get into using your calculator. Of course, if you have a calculator, you can do that, but I want to talk about how could you do this somehow only by looking at the equation and not trying to look at the graph. And the answer is it's usually pretty easy to do this. So I will say usually when I'll say when nothing goes wrong, we find the limit by what our book calls direct substitution. What that means is for, I will just say, just plug in the value. What I mean by that is, in this example, I want to know what does this function approach when x becomes 3? You just plug in 3 to the function. And I said, when nothing goes wrong, that really is the answer to the limit. So here, for that example, that's you can see right at the top there. Well, you can't see it anymore, but anyway, I'm writing it again. x squared minus 6x plus 2. The limit as x approaches 3. Just plug in the value, and by the value I mean the thing down here which the limit is approaching. So I'm going to plug in right here, plug in x equals 3 everywhere for x. So I go 3 squared minus 6 times 3 plus 2. All right, and then whatever that is, that's what the limit is. So this, if you wanted to simplify it, this would be 9 minus 18 plus 2, which is 9 minus 18 is negative 9 plus 2 is negative 7, right? I think I did that right. All right. By the way, this is about the level at which I would expect you to be doing adding and multiplying on the tests. You know, I said there's no calculators on the tests. So this kind of thing, I hope that you feel okay about doing what I just did, which I only marginally feel okay about. I'm actually not terribly good at adding and multiplying numbers. It's not really my thing. But yeah, that's this is the level at which I will expect you to be calculating things on our tests. Okay? Or something, I mean, it could be much more complicated than that, and you could, you know, do much more complicated things if you are using a calculator, but you could even do something like, you know, limit as x approaches 2 of square root x squared plus 1. This would be something like, well, you just plug it in. I plug in 2 for x, which becomes 2 squared plus 1, which is the square root of 5, which on a test or something, I would encourage you to just leave like that. Don't try to tell me what the square root of 5 is. That's the answer. All right? Now, I said that this is the way to do it when nothing goes wrong. So let's talk about what could possibly go wrong when you try to do a limit in this way. Well, there is one major thing that could go wrong. So what could go wrong? What we are principally going to be wary of, in this class at least, is 0 in the denominator. If you get 0 in the denominator, when you try this plugging in thing, then you got some serious work to do, all right? These I would consider, there's not much to it at all. You just plug the number in. Maybe you do a little simplifying if you want to, but that's basically it. You don't have to think very much about it. But if you get a 0 in the denominator, then you have to be a little sort of smarter, or you got to do a little bit more in that case. Like this limit, for example, x approaching 3. And if you try to plug this in, when I try to plug it in, I get 3 plus 1 over 3 minus 3. This is 4 divided by 0. And that is not a number, right? You can't just, you know, dividing by 0 is not allowed. There is no such thing as this. And what is your interpretation of this? When you get something like 4 divided by 0, what that indicates is that this function near this point, x equals 3, looks something like dividing by 0. And the best way to visualize what does it look like to divide by 0 is a graph like this. This is like the 1 over x graph, but I'm drawing it over here at 3 instead. You know, 1 over x is dividing by various values of x. And when you try to divide by 0, what happens is this kind of asymptote thing with the two sides going up and down. And when you see 4 divided by 0, that's an indication that your original function looks something like this. And what is your interpretation of that in terms of the limit? It means the limit does not exist. All right. So I said there's more work to be done, but actually this is not so bad. When you see something like this with a 0 in the denominator, it just means the limit does not exist. And so actually you're done anyways, right? There's not really that much more work to be done. So the moral of the story here is when we get something like a constant divided by 0, where the thing on top is not 0, like 4 over 0, right? Something not a 0 over 0. When we get this, then we can immediately say the limit does not exist. This is a general principle. Okay, I'll put that in a box. When you get a constant divided by 0, where the thing on top is not also 0, then the limit does not exist, and then you're done. You don't have to do any more work. That's just your answer is a DNE. All right. So in this example, you know, the one that I just scrolled off the top there. If you were doing this on a test or something, I would say you just try to plug it in. You get 3 plus 1 over 3 minus 3, which is 4 over 0. And I just say, that does not exist, and that's it. So there's not really any more work to do. You just have to be able to recognize something divided by 0. You say the limit does not exist. The situation when you have to do more work is if you get both zeros on the top and the bottom. Now you have to actually work harder for it. I was very particular here about saying when you get something over 0 where the thing on the top is not also 0. If they're both zeros, then you got problems to discuss. So what if it's 0 divided by 0? There's a special word for that, actually. 0 divided by 0. This is referred to as an indeterminate, I think, form. It's called a form because it's not even a number. Like 0 divided by 0, that's not a legal operation. So this thing is not even a number. But it's an indeterminate form, meaning this tells you nothing about the limit. You don't know actually if the limit does exist or if it does not exist. It certainly does not equal 1. You might be tempted to like cancel the fraction and say this is 1. Don't do that. This tells nothing about the limit. And this is the situation in which you need to work harder, work to simplify. This is the solution. Simplify before plugging in. All right? And this is what you have to do when you end up with a 0 over 0. This is the hard version of these problems. The ones that I've done so far are very easy. You just plug something in and that's the answer. But here you got to work harder. All right? So let's try a few of these. And you should expect, when you have these on the test, they're going to be this harder kind because the easier kind is too easy. All right? Let's try some examples here. How about the limit as x goes to 0 of x plus 3 squared minus 9 over x. All right. Now, you don't know if this is going to be one of the hard ones or one of the easier ones. So what you should do to begin with is just try to plug the value in and see what happens. And if you get just a number for the answer, then that number is the answer and you're done. So let's try and plug it in. Specifically, I'm plugging x equals 0 because you always look at this value down here in the limit, and that's the number that you plug into the rest of it. So what I get 0 plus 3 squared minus 9 divided by 0. Now, I see 0 on the bottom, so I know there's already some funny business going on here. Although if the top is not 0, then I will get just the answer will be does not exist. But actually, the top is 0. If you do remember your parentheses here, you add this first. So this is going to be 3 squared minus 9. But that's 0 over 0, all right? And when you see 0 over 0, this does not mean the answer is DNE, and it's not something else. This means gotta simplify before I plug it in. Simply simplify like that, right? That's what the 0 over 0 indicates. So go back to the beginning. I'm going to rewrite this thing, but simplify. Anybody have a suggestion? What could you do to simplify here? Yeah?
Like maybe factor out what's in the parentheses.
Yeah, use the parentheses here being squared. Think of it like this. 2 of those guys, right? And then actually multiply that out. Expand it out like the FOIL thing. I hope everybody remembers how to do that. Actually, we're going to be doing this exact trick many, many times. So I hope that you feel good about doing the FOIL thing. I'm going to multiply all this out. You go, the first guys, that makes it x squared. The one in the middle is 3 times x. The one on the outside is another 3 times x. And then the one on the end is 3 times 3, which is plus 9. All right? And then I have minus 9 from before over x. All right? I hope that when you write these guys out, I think I meant to say last time, if I didn't, when you're doing your homework or work on the test or something, I don't care if you write down your answers the same way that I write them down. If you've learned to do this or similar things to this in a different way, it's totally fine with me if you want to do it your way, as long as your way is still correct. I would suggest, though, in this case, you should write all of this stuff here. All I did was change this part, but I still wrote all of the other stuff. That's because, like, I'm using an equal sign here. What I write over here should actually be the same as what I write over here. Anyway, that's what I get. Now, can we simplify that at all? I think we can. Actually, this plus 9 and minus 9 will cancel, right? That's nice. Come on. The plus 9 and the minus 9 will cancel. And then one other simple thing I can do is just add the 3x's. 3x plus 3x is 6x. So this is, I still got lim, x goes to 0, x squared plus 6x divided by x. Right? The 9's went away, and I added up the 3's. Okay. I'm feeling all right about this. Anyone have another suggestion about simplifying? You could try actually to plug the value in now. Maybe that's good enough after simplifying, but actually I think you can see what will happen. If I plug x equals 0 here, I'm going to get 0 on the bottom and still 0 on the top. So I haven't simplified enough yet. Any other suggestion? Something you can do here? Yeah?
Factor out the x in the numerator.
Factor out the x in the numerator. I agree. This is a good idea. So what she means is like that, right? It was x squared plus 6x, but those each have an x in them. When you take the x out of them, you end up with x left over and then a plus 6, all right? And an x on the bottom. I like that. What else can we do? This factoring actually allows us to do the next step, yeah?
Aren't you now able to take out the x?
Yes, we can cancel the x on the top and on the bottom, right? This guy and this guy. I don't know if anyone was wondering, why didn't I just cancel the x like right here? Because you can't do that. Don't do that. You cannot cancel things, which are added together. You can't divide them out. But here, since these guys were multiplied, that means I can actually cancel x on top with the x on the bottom. Don't go here and try to cancel one of these x's with that x. Canceling in a fraction does not work that way. All right. So anyway, I end up with, oops, I didn't want to change my color. Having canceled the x's, I get lim x goes to 0, x plus 6 over 1, I guess. I mean, it's just x plus 6, right? The denominator is gone entirely. And now, my friends, we have simplified all the way that we can, and we should try again to plug it in. Hopefully we won't get 0 over 0. I mean, we can't get 0 over 0 because the fraction is gone. And now this equals, 0 plus 6. 6 is the answer. All right. So this one, in my opinion, is far more complicated than the other ones. You have to do quite a few steps to end up with the answer of 6. And this is a good example that demonstrates what I said before. If you begin and you see 0 over 0, that really tells you nothing about what the answer is. It turned out, in this case, the answer was 6, which you wouldn't really see coming just by looking at that. Yeah?
When you're writing the answer, do you have to rewrite the equation and then say equals 6, or can you just say equals 6?
No, it's fine to just say 6 at the end. Oops, off the screen. Yeah, I don't really care if you restate the original thing. Although, another thing that people ask me a lot is, do I gotta write that lim every time? I don't know, as you were copying this down, did you write the lim every time? I would say, I mean, it's a free country, but I think you should write the lim every time. I'm writing equal signs, so that means that each thing is supposed to be the same as what I wrote before. Now, some people, I don't know why, some people are like, yeah, but I just remember the lim. I don't have to write it every time. I just remember it. And I would say, yeah, all right, I guess. I mean, it's like when I write an email, I put spaces in between the words. And somebody would say, wow, why do you put all those spaces? I can still understand it if you leave the spaces out. And I would say, well, yeah, I guess so, but that would be weird. And I mean, we're writing these things down for a reason, right? Because they're supposed to represent some kind of truth about something. So if you want it to be correct, what you're writing, you should write the lim every time. Now, I'm not going to take out points for that, but I would consider it socially weird to just decide not to write certain parts of the equation just because you don't like to. All right? Like, did you write the bar in every fraction? Yeah. If you didn't write, nobody ever asked me, do I have to write that fraction bar every time? I would say, kind of. I mean, I guess you don't have to, but I would wonder about you. All right. Any thoughts about that? Let's just try a couple more examples. These are fairly complicated, in my opinion. So I got 2 more of those, and then maybe 3 more, and then I have some for you all to try also. Let's try lim x goes to minus 3, x squared plus 5x plus 6 over x squared plus 2x minus 3. All right. Don't think too hard about this. You should begin by trying to plug the value in and see if you get an answer immediately. In that case, this is an easy one, right? But we don't know just by looking at it. So I'm going to try to plug in. I'm plugging x equals -3. So it looks like minus 3 squared plus 5 times minus 3 plus 6 divided by minus 3 squared plus 2 times minus 3 minus 3. All right? These are easy to screw up, unfortunately, the numbers, but I hope that we don't screw them up. Go through, okay, -3 squared is 9. 5 times -3 is -15 plus 6, like that. So this is what I get for the top, 9 minus 15 plus 6. And then on the bottom, I get 9 minus 6 minus 3. And those are actually 0 and 0, all right? So that means we cannot just stop immediately and get our answer. You have to do some more work here, all right? So go back to the beginning and try to simplify this thing. What do you think for simplifying? Anybody see anything promising? In the previous example, we had something that was squared and we expanded it. This one, you need a slightly different but closely related trick. Yeah?
You could factor.
You could factor, yeah. I think you should factor on the top and on the bottom. I hope you remember your factoring. Actually, this is going to be very, very important in this class. So if you are a little rusty on the factoring, you might want to de-rust yourself before too long. I'd be happy to chat about it if anybody wants to go over the basics. But up top, I want to factor, and actually I'm going to factor on the bottom. That means you turn one of these big guys, turn one of these big guys into one of these products of 2 little guys. I'm going to do that on the top and the bottom. So on the top, it's going to be an x and an x. And then the other 2 numbers need to be chosen so that their product is 6. It's 6 when you multiply them, and it's 5 when you add them up. I think 2 and 3 will do the trick for this one. All right, so this is x plus 2 and x plus 3. People learn how to factor in different ways. I don't know how you learned, but I learned by just sort of guessing the numbers. All right, and for the second one, I have the fact that this 3 is negative in this position means that these 2 numbers are going to be, one will be a plus and one will be a minus. And again, they have to multiply to be 3 and add up to 2. Can anybody say? What should they be? 3 and negative 1. Yes, I agree. Plus 3 minus 1. All right? That is some simple factoring. This, like I said, is going to come up all the time in this class. So I hope that you are comfortable with doing factors like that. And lucky for us, after factoring, you can see that some of this is going to cancel. The x plus 3 on the top and the x plus 3 on the bottom will cancel. All right, so after doing that cancellation, it's lim x goes to minus 3, x plus 2 over x minus 1. And that actually cannot be simplified anymore. Don't try to cancel the x's or something. That's not going to work. We should just try to plug the value in again at this point. So I'm going to plug this in. I get -3 plus 2 over -3 minus 1. That's -1 over -4. 1/4 is my answer. All right, that's how we do it. Anybody got questions or thoughts about that? All right, I just got, let's do one more of these, and then I got one for you all to try. How about, this is similar, but you'll see it goes a little differently. All right. So again, we should begin by trying to plug in this value. We get -3 squared plus 5 times -3 plus 6 divided by -3 squared plus 6 times -3 plus 9. Don't forget your parentheses. When you square a negative number, you end up with a positive, right? So this is 9 minus 15 plus 6. And on the bottom, 9 minus 18 plus 9. This again is 0 over 0, which means we'll have to go back and simplify. So this thing here, it's supposed to be a little arrow. Doesn't look like it. This thing here. How do we simplify? We should factor on the top and the bottom. Actually, the top that I'm using here is the same as the previous example. So this factors as x plus 3 and x plus 2, just like before. The bottom, can anybody say what the factors on the bottom are?
X plus 3 and x plus 3.
Yeah, 3 and 3. Excellent factoring. All right, those are the factors on the bottom. Now we can cancel. The x plus 3 on the top cancels one of the x plus 3's on the bottom. We end up with lim x goes to -3 x plus 2 over x plus 3. And now we try to plug it in. After having simplified as much as you can, you try to plug the value in again. Here we get -3 plus 2 over -3 plus 3. This is -1 over 0. And what is your interpretation of that?
It doesn't exist.
That means the limit does not exist. Remember the thing that I wrote in the box a while ago? If you get something over 0 and the thing on top is not a 0, that means the limit does not exist. And so my answer for this one is just the original limit does not exist. All right. That's how we do it. These ones do require some work, and unfortunately it's fairly easy to mess it up on the inner steps there. So what can I say about that? Don't mess it up. I don't have any life advice. All right, let's try a few. I got some for you to try. Oops. This first one is an easy one. I got 4 of them here. Oh, nope, I got 3 of them, sorry. All right, see what you think. They will take far more space than what I just left you here. Maybe I'll try and put one of those on the same screen. this, you did these numbers, right? It's 0 on the bottom.
Yes, here.
Okay. Yeah. Yep. You good? Yeah, that's good. Alright. Yeah, so what does that mean? This means that we're going to define this. You only have to go back and simplify it. 0 over 0. It's simplest over 0. And you're done. Alright. Okay. I give you another minute and then we can talk about them. Something divided by 0. It's not 0 over 0.
Oh, okay.
0 over 0, that's what it's about.
Oh,
Good? All right, can we talk about these? I don't know if everybody's finished yet, but it's all right. Most people seem to be doing good. So the first one actually is quite straightforward. All you got to do is just plug the value in. You get -1 squared plus 4 times -1, which is 1 minus 4, -3. I hope everybody agrees. The first one is -3. The second one is a little more taxing, although it's not so bad. This one, again, you should start by trying to plug the value in. You get 3 squared plus 4 times 3 minus 2 over 3 minus 3. This is 0 on the bottom. On the top, it's 9 plus 12 minus 2. Right? 9 plus 12 minus 2 is that 19?
Yes.
You can tell I'm not terribly good at that. Anyway, 19 divided by 0. What is your interpretation of this? You say the limit does not exist. Remember the thing that I wrote in the box all the way up here? When we get something over 0 where the top is not a 0, then the limit does not exist. So you do not have to go back and simplify or anything like that. Actually, this is slightly a trick because this one, it looks like you can factor, but you can't. Actually, there is no factors of that. So this one is a DNE. That's the second one. Let's try this last guy. This one, you really do have to sort of go through all of the business about resimplifying and canceling stuff. But anyway, you should start by trying to plug this in. 1 squared plus 3 times 1 minus 4 divided by 1 minus 1. This is indeed 0 over 0, which means I need to go back here and simplify. The proper thing to simplify would be factoring in the top. And as I was going around, I saw most folks said this, x plus 4, x minus 1 on the top. And I have x minus 1 on the bottom. Then you can factor the x minus 1's. One thing you might wonder, this is kind of magical that this actually worked, that I could factor it out, and by some magic, one of the factors actually ended up equaling the thing on the bottom. What if that didn't happen and I couldn't cancel them? The answer is, then you messed it up somehow. This kind of magic actually is guaranteed to happen when you get 0 over 0. So if you do factor but they don't cancel, it means either you factored it wrong or you actually didn't get 0 over 0 in the first place, and you shouldn't have been doing this at all. Because if you don't get 0 over 0, then you don't have to do any of this. Anyway, this having canceled, I end up with lim x goes to 1 of x plus 4, and the answer is 5 when you plug it in. All right. Notice I wrote the lim every time except here. Why didn't I write lim in this step? That's because lim is like an operation. In this step, I did not do the limit yet. In this step, I still did not do the limit yet. The limit actually happens when I plug this number in. I plugged in 1 for x, and now the limit as an operation has occurred in this step, which is why I don't write lim anymore. All right. Any thoughts about that? I hope, as I was going around, it seemed like people were doing okay with this, so I hope it seems to make sense to everybody. One last thing about this is basically all that I want to say about limits algebraically. That's the second thing on the list. One last thing is sometimes there's, I put the apostrophe in the wrong spot. Come on now. Sometimes there's extra variables in there. I'll show you an example of what I mean. And the answer, what you should do in that case is just leave them, and they appear in the answer, unless they magically cancel somehow. Sometimes there's extra variables inside there. You should just pretend that they're like numbers or constants, and they will end up existing in the final answer. So here's an example like that. This is very strange looking, but actually this kind of limit comes up when we are eventually going to talk about the derivative, which is our major topic for this semester. The definition of the derivative often involves limits that look like this, where there's actually, if you look closely here, there are two different variables in here. There's the x and the h. And the h is the one, in this case, that I'm taking the limit with, all right? So that means the x, so we'll do the limit, by plugging in h, right? Because h is the one that's down here. The variable which we're doing the limit of is the h. The x is just another thing which is going to stay in there forever, and probably there will be some x's in our answer. So we'll do the limit by plugging in h. X is treated like a constant, and it will appear in the answer. You don't ever plug in for x in a problem like this. The x is just the x, and it stays the x until the end. All right? Anyway, we can still do all that same stuff that we did before. It's just a little, it will look slightly more complicated. So I begin by trying to plug in h equals 0. So this whole thing here, when I plug in h equals 0, I get 2x plus 0 squared minus 4x squared divided by 0. That is plugging in h equals 0. The bottom is 0. What about the top? Let's simplify that a little bit. So 2x plus 0, I don't even care about this, plus 0. I have 2x, the whole thing squared, ends up becoming 4x squared minus 4x squared. And that is 0 over 0, which means we have to go back and simplify the original thing before continuing. I hope everybody's okay with this step that I did here. 2x, the whole thing squared, you have to square the 2 and also square the x. You get 4x squared. All right, so got to simplify. That's what it means when you see 0 over 0. So I go back to the original thing. I'll just write it again here. 2x plus h squared minus 4x squared over h. What can I do to simplify here? Anybody got a suggestion? Yeah.
You're gonna FOIL.
Yeah, do the FOIL thing on the first part there, the parentheses with the squared. I'm going to multiply that out. So it's going to be I'll write it sort of side by side. By the way, if you're some kind of FOIL master and you can do these intermediate steps in your head, that's totally fine with me. I'll write it out. I'm not trying to impress anybody. So in the FOIL right here, I'm looking at this part, right? You go, the first two things, 2x times 2x, that is 4x squared. The inside product is h times 2x, and the outside is 2x times h. Those are the same. So it's 2x times h and another 2x times h. That's the inside and the outside product. And then the last product is h times h, which is h squared. All of that stuff, followed by minus 4x squared and divided by h, all right? So that stuff, which like the pink stuff, turned into that pink stuff. Don't forget to also write this part. This is something that I see a lot of people who don't like to write the whole thing every time. They forget, oh yeah, there was this other thing, which becomes important. Anyway, what should we do to simplify? Hopefully this will simplify. I can see one simple thing up top. I see 4x squared and a minus 4x squared. So those will cancel. So I can cross those out. 4x squared and minus 4x squared cancel. Nothing else obviously cancels, so I'm just going to write the rest of it again. What remains is 2xh plus, actually, would you mind if I add those up, right? 2xh plus another 2xh, they add together, we get 4xh, right? I got two of those and two of those, makes four of those. 4xh minus, there's no minus, plus h squared. That's all that was left, right? All right, we're getting somewhere. There's one more simplification that can be done here. Yeah?
The h's.
Yeah, we got the h's. Everything on top, the top is two things added together, but they both have an h on them. So I can factor the h out of each. I go h, and then what's left is 4x plus another h divided by h. That is factor the h. And now we can cancel h on top and h on the bottom. When you do these problems enough, you will realize this is always sort of your big breakthrough step is when you actually cancel the denominator. That means you are in good shape to actually arrive at an answer. Because after all, the denominator was what was causing all the problems to begin with, because we ended up with the 0 over 0. But once you kill the denominator entirely, there's no opportunity for any more funny business. Oops, sorry. So I get lim h goes to 0. All that remains is this, 4x plus h. And my final step is to actually do the limit by plugging in h equals 0, and I get 4x plus 0, which is 4x, the end. All right. I will point out again that I wrote lim every time until this step. That's because this is the actual step at which I did the limit by plugging in h equals 0. And I do not write the lim anymore because I already did the lim. All right. Sometimes I get people who write the answer like this. Lim h goes to 0, 4x. This I would say, don't do that. I mean, I know what you mean, but you shouldn't write the lim as part of the answer. The lim is an operation that you actually did in this step, so you don't write it anymore. This is kind of like saying, if I ask you, what's the square root of 4? And you say, square root of 2 is the answer. I would say, no, the answer is 2. And you'd be like, oh, yeah, but I did the square root, so I put the square root there. It's just like I did the square root. No, if you did the square root, you should not put it there, because that means something else, all right? So don't do that. Don't do that either. Do that. Don't write the lim after you did that as an operation. All right? Any thoughts or feelings about that? This is finding limits algebraically. This one requires some, algebra skills, unfortunately. I hope that you're feeling good about your algebra skills. All right, great. I think we can move on to the next bit then. That was limits algebraically. We got 15 minutes left. We can get started on something else. I want to talk about Limits at infinity. Limits at infinity. What I mean by this is stuff like lim x approaches infinity. This is something that we can talk about, and it's not so difficult to discuss. Lim as x approaches infinity. What that means, of course, infinity is not a real number, but it is a thing that we can talk about. It's sort of an abstract thing which represents x getting really, really big. So what this means, if I put, sorry, I'm going to put a f of x in there. Lim as x approaches infinity of f of x. What does that even mean? Since infinity is not a number, you can't say, like, actually x cannot really approach infinity. It doesn't get really close to infinity because there's no such thing as close to infinity as far as numbers goes. But what that does mean, this means which y value does f of x approach as x increases forever? All right? The x itself is not actually approaching a particular point. It's going up and up and up forever. And the question is, what is the y value that f of x approaches when the x increases forever? Actually, there's sort of another word for this that I think you're familiar with, but here's an example on a picture. Let's say I have a function that does this. This is a function that looks vaguely like 1 over x. Goes like that, up there, all right? On this picture, what is lim as x approaches infinity? So here, on this picture, lim x approaches infinity of f of x, whatever that function is. What it means is I look at x values just way out to the right side. What happens as the x goes off to the right forever? Does the function approach a particular y value? Anybody think it does? I think it does. Yeah? I don't think 0. If it's approaching 0, that would mean this line eventually goes down to the x-axis, which is not what I intended on my picture. I wanted for this line to kind of look like this. Oops. I'm trying to draw an asymptote here. Right? That's where that line is supposed to go. So as the x goes out to the right forever, maybe it wasn't clear on my picture, the y value doesn't actually go down to 0. It goes to 1, I think. I saw someone whispering to themselves. 1. Yes, the answer is 1 here. All right. I said that there's some sort of language that you're already familiar with. Another way of saying this is just that f of x has a horizontal asymptote. As x goes to the right. And that asymptote is, the tote is on y equals 1. That's what it means. This is another way of saying what the limit at infinity means. All right? And if you, I know some people are like philosophically uncomfortable with the idea of infinity. I'm not really trying to talk about infinity. All I'm saying is that this has a horizontal asymptote, all right? And you don't have to say the word infinity to talk about horizontal asymptotes. The way that we write that, we do write it using the infinity symbol. But what this little thing means here is just I'm asking about what are the horizontal asymptotes of this function. Now in this case, I approach y equals 1 when I go off to the right. What about when I go off to the left? It also approaches y equals 1 when I go off to the left. So in this example, and this one, also lim as x goes to minus infinity equals 1 again. And that's because of this asymptote. That side of the horizontal asymptote. all right? This tote is what I wrote down there. All right, this is what we call the limits at infinity. They really just represent horizontal asymptotes. Now, when you're looking at a graph, again, it's easy to look at a graph and say what the limits are. What's more interesting is if I just show you equations, can you tell me what the various limits of equations are? So let's talk about that. So how do we do this? How do we find limits at infinity from equations? And there is sort of a series of simple tricks which culminates in one very nice simple trick which makes these questions very, very easy if you know what to look for. I'm going to try and sort of build up to what the trick is, but there's some basic rules here. One of them is if I have a limit as x goes to infinity of some kind of power of x, this limit, so a power of x, I'm talking about, x squared, x cubed, x to the 4. If you recall, all of those functions basically look like this, or maybe they look like this from the left side. In a x cubed, the left side goes down. In a x squared, the left side goes up. But anyway, both of the right sides, they always go up in a polynomial like this. These ones depend on, it could be going up or going down to the left, depending on what the n is, if the n is even or odd. I hope you remember some vague rules about this. But anyway, this does not exist. That's because a function like this does not have a horizontal asymptote. All right? It always looks like this kind of thing or this kind of thing. In either case, it doesn't have any horizontal asymptotes when I go either to the right or to the left. So this does not exist. That's because there is no horizontal tote. And so the limit as x goes to infinity does not exist. And also, the limit as x goes to minus infinity does not exist. All right? Another way to say that, if you'd like, is what happens if you take a power of a really, really big number? The answer is it again becomes really, really big. It doesn't actually approach any particular value. If you're taking powers of super big numbers, you just get more super big numbers. There is no value that they approach. All right? That's the first of my basic rules. The second of my basic rules is what if you had the same thing but it was in a denominator? And what if it was lim x goes to infinity 1 over x to the n? All right? Now in this case, you have to keep in mind what I just said. If you really have, we're trying to imagine x is way out to the right, or x is like a really, really big number, then what does this look like? This looks like 1 divided by some really, really big number. If you know anything about fractions, I'm talking about like 1 divided by a million, or 1 divided by a billion. Those things are basically 0, right? 1 divided by some very, very big number is going to be really close to 0. And if you think about in this limit, as x goes big forever, this quantity will get closer and closer to 0. So this thing is 0, all right? And also x going to minus infinity. It's the same. So in the case of minus infinity, what you're talking about here is 1 divided by a really big number, although it might be a really big negative number. But it doesn't matter. You're still going to get 1 divided by something giant, which is still going to be close to 0. So this is also 0. All right? These are the basic tricks which you need to keep in mind. And if you can remember those basic facts, these guys and these guys, right? Basically, if you have x in the denominator, that part is going to be 0. If you have x in the numerator, that part, the limit does not exist. All right? Let's just try sort of a simple one here, or a simple thing to talk about. How about limit x goes to infinity, 1 over x squared plus 2 over x plus 3. All right? These are 3 things added together. I'm just going to sort of go down the list and say, what is each of these limits as x becomes infinite, as x gets really, really big? This one right here is exactly what you see right there. I get 0 when I do this limit. All right? So if I were to write them kind of one at a time, the first one is 0. The next one I have 2 divided by x. Now in this box that I put here, I only did like 1 divided by x. But this 2 divided by x is the same as 2 times 1 over x, right? And that 1 over x is also becoming 0. This is really more like 2 times 0. That's because this 2 stays as a 2, but the rest of it, which is 1 over x, becomes 0. And then 3, what becomes, what does 3 approach? That's just 3, right? There was no x there, and so this part does not become 0. It's just 3. And so my answer here is 3. Huh? 3. I said it right. 0 plus 0 plus 3 is 3. All right? You do each limit separately and then add them together. Yes?
What if you gave us one of like the equations where the limit does not exist for one of them? Would it make the entire like limit not exist?
Yes, I'm actually going to do some more complicated ones now, but yeah, if you had, so if you do this kind of one at a time thing and you see some of them do not exist but some of them do exist, that actually is still ambiguous. It's not doesn't necessarily mean the whole thing does not exist. So yeah, you do have to do a little bit more work sometimes. Let's try, I got an example here. And these, we're going to do some more like this next time. We've only got a couple of minutes left. All right. Now the problem with this actually is, I don't know if this is exactly what she had in mind, but in this example, if you just try to plug these things in, if you just try to do them sort of one at a time, I'm going to do this in red because this is going to be bogus what I'm writing here, but you might be tempted to just look across the top and say, okay, x is like x to the 1, so that would fall in this category. That's a DNE. So you might be tempted to just write like, oops, sorry. That first part is like a DNE and then plus 4, I guess, and then over here I get a DNE minus 1. This is bogus though. There's no such thing as like DNE plus 4, all right? So when you see this kind of stuff, it means really you need to think differently about what you started with. And there is a trick in this case. The trick here is to divide everything on the top and the bottom of the fraction by x. All right. The idea is to change it so that all the x's are in little denominators of things. What this becomes, if I divide everything by x, is x over x plus 4 over x divided by x over x minus 1 over x. And then some of these will cancel. The x over x is 1. That's a 1 plus 4 over x over 1 minus 1 over x. All right? And now all the x's are in little denominators. And the purpose of this is that now we can actually do sort of what I tried to do in red here, although I got a bunch of DNEs. If you try to do the same thing, though, you will not get any DNEs at this point. They become zeros. So here, I can evaluate the limit. I get 1 plus 0 divided by 1 minus 0. And the answer is 1. All right. In this last step here, I turned 4 over x into 0 because when you take the limit at infinity and x is in the denominator, you're going to get 0. All right. I think maybe we'll leave it at that. We're going to do a bunch more examples just like that. And you should look out for our first homework assignment, which will be due on Tuesday evening. I'm going to post the assignment sometime before the end of today, based on how far we got. All right, I hope you have a good weekend. See you next time.